In this tutorial we learn to create and interpret a seismic chimney cube. In this seismic dataset from the Gulf of Mexico we have identified a prospect with a clear amplitude anomaly. The question we will address in this tutorial is whether or not to drill this feature. We will answer this question by studying the fluid migration paths with the help of a chimney cube. When oil, gas or water migrates upwards through a sequence, rocks are cracked and chemically altered, and connate gas may stay behind in the pores. Such fluid migration paths show up in seismic data as vertically disturbed noise trails. To study these trails and their spatial relationship to other elements of the petroleum system, we create a chimney cube. This is a cube that is generated by a neural network that was trained on attributes extracted at example positions picked by the user. We need two sets of input locations, one representing chimneys, here in green, and the other one representing non-chimneys. It has normal seismic background response, positions that are not affected by fluid migration. The non-chimney examples in this case are the blue locations. In the neural network module, we select all current attributes as inputs. These attributes are based on the default set that was loaded in the attribute set window. As targets we select the two pick sets containing our examples of chimneys and non-chimneys. We set the percentage for the test set to 30%. These examples will be used to check the performance of the network during training. They are not used to update the weights of the network. Weights are only updated using examples from the training set. Now press OK. At this point all selected attributes are extracted at all picked locations and the examples are split into a training and test dataset. We can do some cross-plotting and editing in this spreadsheet, but here we will continue to start neural network training. In the upper left graph we see the normalized RMS error for training and test sets going down during training. Training can be stopped when the curves flatten off. The optimal point to stop is when the error on the blue curve, it has the test dataset, is minimal. The lower graph shows the percentage misclassification, here less than 5%, which is very good. On the right we see the input attributes. The color scheme indicates the relative importance of the input attributes, ranging from white via yellow to red, with red being the most important. We can use these colors to tune our network and remove input attributes that will require extra CPU time without contributing much to the end result. After saving the network we can now apply it to any element in our system, or we can create a chimney cube in batch mode. Note that our neural network has four possible outputs: chimney neck, chimney pass, classification and confidence. Chimney neck and chimney pass are the actual outputs of the neural network nodes. These are mirror images of each other. If one is close to 1, the other will be close to 0. In a two-class problem like chimney neck or chimney pass, we output the chimney pass node. The higher the value of this output, the more likely it is that the position belongs to the chimney pass class. The output therefore is a chimney probability cube. Once we are satisfied with the test result on one inline, we create a chimney cube for the entire volume. To interpret this cube, let us look at some volume rendering results. Here we see a salt dome, two areas with high amplitude anomalies, and chimneys above the salt dome. An initial interpretation could be that hydrocarbons are generated deep down in the basin, they move up against the salt dome, and then move straight up to charge the first level of reservoirs and creating amplitude anomalies here. But they also leak from these levels upwards to charge our main feature of interest, resulting in an amplitude anomaly also at this level. But again there is leakage all the way to the seabed. Let us first look at the seabed reflection. We have marked a red spot on the seabed. If we zoom in, we see that there is a small mound at this position. This is a mud volcano, which is direct evidence that something is bubbling up from below the seabed. When we toggle the seabed off, we see that one of the chimneys is ending up exactly under the mud volcano. This is strong evidence that we have indeed visualized fluid migration paths. Now let us look at our feature itself. We have mapped the top of the feature. And the shape of this very much looks like the mud volcano at the present day seabed. In fact, we interpret this as two paleo mud volcanoes and a mud flow. This interpretation has two important implications for our interpretation of the petroleum system. First, the reservoir quality may not be very good, and second, when this was the seabed there was active hydrocarbon migration going on. In other words, Our petroleum system has at least 2 pulses of active hydrocarbon migration, one when our feature was formed and one at present day. This still does not answer our question whether or not we should drill this feature. For this we will look at faults and chimneys immediately above our prospect. On this horizon we have visualized the faults by calculating the similarity attribute along the horizon. If we now overlay the response of the Chimney Cube, we see that the chimneys are following the fault pattern and that they lie directly above the prospect. With this observation we can now answer the question. Based on many case studies we've come up with a chimney classification scheme that can be used for prospect ranking. The prospect we have studied falls in the class we call fault leak trap, which is characterized by chimneys associated with faults at the crest of the structure. This class has only a 1 in 4 chance of finding hydrocarbons in commercial quantities. Given the deep offshore location we are talking big bucks and high risks. Hence in this case we would recommend not drilling this prospect. Note that some of the other classes have much higher success ratios. The technology is widely applicable. DGB has conducted chimney interpretation studies in many basins around the world. Over 90% of all the tertiary and Mesozoic fields evaluated to date are associated with chimneys. This concludes this tutorial on the Chimney Cube.